What if I told you that right now, at this very moment, somewhere in the universe, someone is stepping out of a machine that doesn't just move through space, but through time itself? Think about the grandfather paradox, where a time traveler goes back and accidentally prevents their own existence. Or the mind-bending twists of films like Back to the Future, where a single change in the past ripples into a completely unrecognizable future. These aren't just wild fantasies, they're glimpses into a question that has haunted scientists, philosophers, and dreamers for centuries. Is time travel really possible? The idea of bending time, of slipping between moments like turning the pages of a book, feels like pure science fiction. Yet some of the brightest minds in physics argue it might not be as far-fetched as we think. From black holes warping the fabric of space-time to quantum particles that seem to defy the arrow of time, the universe is full of mysteries that hint at something extraordinary. And that's exactly what we're diving into today: 30 groundbreaking theories that could explain how time travel might actually work. Some are rooted in hard science, others border on the edge of imagination, but each one opens a door to a world where the impossible starts to feel tantalizingly close. This isn't just about wild speculation, it's about exploring the very boundaries of reality. What if time isn't the rigid, unbroken line we think it is? What if, hidden in the equations of Einstein or the strange behavior of subatomic particles, there's a key to unlocking the fourth dimension? Over the course of this journey, we'll unravel theories that stretch from the depths of cosmic phenomena to the quirks of quantum mechanics, each one offering a unique piece of the puzzle. Whether you're a skeptic or a believer, one thing's for certain: by the end, you'll never look at time the same way again. So buckle up, we're about to take a ride through the most thrilling ideas that could turn time travel from fiction into fact. Einstein's theory of special relativity turned our understanding of time upside down by revealing it isn't the fixed, universal constant we once thought. Imagine two identical twins. One stays on Earth while the other rockets through space at nearly the speed of light. When the traveling twin returns, they'd be younger than their Earth-bound sibling. This isn't science fiction, it's the twin paradox, a real consequence of time dilation. The faster you move through space, the slower time passes for you relative to someone standing still. Astronauts on the International Space Station experience this on a tiny scale, aging milliseconds less than people on the ground. But crank up the speed close to light's limit and the effect becomes dramatic. A 10-year journey at 99% light speed could mean returning to find decades or even centuries have passed back home. This isn't just about clocks ticking slower, it's about the fabric of reality itself. Special relativity shows that space and time are woven together into a single flexible sheet called space-time, and motion warps it. The implications for time travel. If you could build a ship capable of sustained near-light speed travel, you'd effectively leap into the future. But here's the catch: while this lets you race ahead, it doesn't let you go backward. You can't revisit the past this way. Still, the idea that velocity alone can bend time reshapes our thinking about what's possible. Think of space-time like a river. The faster you swim against the current, the closer you get to light speed, the more the flow of time resists you. This is why nothing with mass can ever reach light speed. It would take infinite energy. But what if we could cheat the system? Some theories suggest exotic matter or cosmic shortcuts might one day allow it. Until then, special relativity gives us the first concrete glimpse of how time travel might work. Not with magical machines, but with the sheer physics of motion. The universe, it turns out, already has a built-in time machine. We just need to learn how to steer it. If special relativity shows us how speed bends time, general relativity takes things further, revealing that gravity itself might hold the key to traversing the cosmos in ways that defy clocks and calendars. Picture spacetime not as a flat, rigid grid, but as a stretchy fabric warped by massive objects like stars and planets. A bowling ball placed on a trampoline creates a deep dent. That's gravity at work. Now imagine folding that trampoline so two distant points suddenly touch. This is the essence of a wormhole, a cosmic shortcut where space bends so dramatically that two separate moments in time could connect. The idea isn't just speculative. In 1935, Einstein and physicist Nathan Rosen proposed the Einstein-Rosen bridge, a theoretical tunnel through spacetime. These bridges emerge from the math of general relativity, suggesting that under extreme conditions like near a black hole's crushing gravity, spacetime might pinch and fold, creating passages to other times or places. Sci-fi has run wild with this, from Interstellar's Gargantua to Stargate's portal networks, but the real science is even stranger. Some models suggest wormholes could link not just distant locations but different times, turning them into natural time machines. Yet here's the catch: wormholes, as far as we know, are incredibly unstable. Without something to prop them open, they'd collapse instantly, crushing anything trying to pass through. That's where exotic matter comes in, a hypothetical substance with negative energy that could theoretically counteract gravity's crush. Think of it like cosmic scaffolding, holding the wormhole's throat open long enough to slip through. The problem: we've never observed exotic matter, and the energy required might dwarf anything we could produce. Even if we solved that, wormholes come with paradoxes. Step into one end, and you might emerge before you left, creating causality loops that scramble cause and effect. Physics abhors paradoxes. They hint at missing pieces in our understanding. Still, the mere possibility that spacetime could be threaded with these shortcuts reshapes our view of reality. It suggests the universe might be far more interconnected than we ever imagined, with hidden tunnels weaving through the cosmic fabric. So while wormholes remain in the realm of theory, they're a thrilling reminder. The universe's rulebook isn't just flexible, it might still have pages we haven't even turned yet. And if we ever crack the code, the past and future could become just another destination. If wormholes tease us with cosmic shortcuts, closed time-like curves throw the rulebook out entirely, suggesting time might loop back on itself like a twisted ribbon. In Einstein's equations of general relativity, there are peculiar solutions where spacetime bends so severely that a path could circle back to its own past. Picture walking in a straight line only to find yourself right where you started, not just in space but in time. These paths, called closed time-like curves, aren't just mathematical oddities. They're blueprints for time machines hidden in the fabric of the universe. Take Gödel's rotating universe, a model proposed by mathematician Kurt Gödel in 1949. In a cosmos spinning fast enough, spacetime itself would twist into helical shapes, allowing a traveler to follow a curve that returns to an earlier moment. No exotic matter, no wormholes, just pure geometry bending time into a circle. The catch: our universe isn't rotating anywhere near that speed. But the sheer fact that Einstein's equations permit such loops forces us to confront a radical idea. The universe might allow time travel without breaking its own rules. Enter Stephen Hawking's chronology protection conjecture, a cosmic safety net. Hawking argued that even if closed time-like curves exist, nature would conspire to prevent paradoxes. Quantum effects, like vacuum fluctuations near a time loop, could escalate into infinite energy, shredding the curve before it forms. Think of it as the universe's immune system, attacking anything that might create a logical inconsistency. Yet not all physicists agree. Some propose that quantum mechanics could tolerate paradoxes through mechanisms like self-consistent loops, where events adjust to avoid contradictions. Imagine shooting your past self, but the gun jams or you miss. The universe would correct itself to preserve causality, like a river rerouting around a rock. The debate gets even wilder with recent work on retrocausality in quantum physics, where particles seem to influence events backward in time. It's as if the universe is subtly hinting that the arrow of time might be more flexible than we thought. While closed time-like curves remain theoretical, they force us to grapple with profound questions. Is time travel inherently self-defeating, or is the cosmos stranger than we dare imagine? One thing's certain, the line between science and science fiction has never been thinner. What if you could build a time machine not with exotic matter or wormholes, but with something as simple as a spinning cylinder? Enter Tipler's rotating cylinder, a mind-bending concept where sheer rotation warps time itself. Proposed by physicist Frank Tipler in 1974, this theory suggests that an infinitely long, ultra-dense cylinder spinning at nearly the speed of light could twist spacetime into a loop, creating a path to the past. Picture a cosmic drill boring through time, its rapid spin dragging the fabric of reality around it like honey stirred by a spoon. If you circled this cylinder in a carefully calculated spiral, you'd find yourself returning to a moment before you even began the journey. The math behind this is rooted in Einstein's equations, showing how massive rotating objects distort spacetime. The cylinder's immense density and speed would generate a frame-dragging effect so extreme that time would coil around it, forming a closed time-like curve. Think of it like walking against a moving walkway, except the walkway is time itself, and the cylinder's spin is the force pulling it backward. It's a tantalizing idea, suggesting time travel might not require black holes or quantum tricks, just engineering on a cosmic scale. But here's the hitch: the cylinder would need to be infinitely long to avoid gravitational collapse at its ends, and the materials required don't exist in our universe. Neutron stars, the densest known objects, come close, but even they can't spin fast enough without flying apart. Critics also point out that an infinite cylinder is impossible to construct, placing Tipler's idea firmly in the realm of mathematical curiosity. Yet it's more than just a thought experiment. The theory reveals how rotation, something as mundane as a spinning top, could, under the right conditions, unravel time's linearity. Even if impractical, Tipler's cylinder forces us to confront a profound truth. The universe's rulebook might allow time travel in ways we haven't yet imagined. It's a reminder that sometimes the most outlandish ideas are the ones that push science forward. Who knows, one day we might find a way to shrink this concept down to size, or discover something even stranger lurking in the equations. Quantum mechanics upends our everyday notions of time with experiments so bizarre they'd make even Doctor Who question reality. At the subatomic level, particles exist in a haze of possibilities called superposition, where an electron can spin both clockwise and counterclockwise simultaneously until measured. This isn't just theoretical. The famous double-slit experiment shows particles behaving as both waves and particles, their final state collapsing only when observed. Now imagine this applied to time itself. Delayed choice experiments reveal something astonishing. A particle's behavior in the present can be influenced by a measurement made in its future. It's as if the universe is working backward, rewriting history based on decisions yet to happen. Take physicist John Wheeler's cosmic-scale version of this experiment. Light from a distant quasar bends around a galaxy, creating multiple paths to Earth. By choosing whether to measure the light as a particle or wave after it's traveled for billions of years, we seemingly force it to have behaved one way or the other all along. Time, in this quantum context, isn't a straight line but a tangled web where cause and effect blur. The observer effect adds another layer of strangeness. In quantum systems, observing a particle doesn't just reveal its state, it creates it. Some interpretations suggest reality remains undefined until conscious observation locks it into place. Extend this idea to time travel, and you're left with a dizzying possibility. The past might not be fixed at all. A time traveler's observations could retroactively reshape events, like a cosmic game of Jenga where every move alters the tower's foundation. Critics argue these effects apply only to the quantum realm, not macroscopic objects like humans or time machines. But breakthroughs in quantum entanglement, where particles instantly influence each other across vast distances, hint that spacetime's structure might be more malleable than we think. If quantum phenomena can ignore classical limits of space and time, who's to say we can't harness them? The frontier of quantum mechanics keeps whispering one tantalizing clue: time, at its core, might not play by the rules we think it does. What if every choice you make doesn't just alter your future, it spawns an entirely new universe? The many worlds interpretation of quantum mechanics proposes exactly that, a cosmic kaleidoscope where every possible outcome plays out in its own branching timeline. Forget the idea of a single, linear past and future. This theory paints reality as an infinite tapestry of parallel worlds, each one a ripple from every decision, every chance event, every quantum fluctuation. And here's where it gets wild for time travelers. If you could somehow hop between these branches, you wouldn't just be moving through time, you'd be surfing the multiverse. Take Schrödinger's infamous cat trapped in a box with a 50-50 chance of survival. In the classic thought experiment, the cat is both alive and dead until someone opens the box and collapses reality into one outcome. But Many Worlds flips the script. There's no collapse, just two separate universes, one with a purring cat, another with a tragic end. Both are equally real, unfolding simultaneously in a web of diverging timelines. Now imagine you're a time traveler stepping into that box's past. Your presence could nudge events, say, accidentally bumping the poison vial, creating yet another branch where the cat's fate shifts. You haven't rewritten history, you've simply added another thread to the ever-expanding multiverse. This reshapes the grandfather paradox entirely. Instead of erasing your own existence by altering the past, you just fork off into a new timeline where your actions play out differently. Kill your grandfather, that version of you vanishes from that branch, but the original timeline where he survived chugs on untouched. It's like a cosmic undo button, messy for the version of you in that new reality, but the universe as a whole shrugs and keeps spinning out alternatives. Critics argue this is less time travel and more universe hopping, yet the implications are staggering. If every quantum event spawns new worlds, then every moment is a crossroads. The you reading this now might be one version among countless others, each living out different choices in parallel dimensions. Somewhere out there, dinosaurs never went extinct. Somewhere else, you took that job abroad. The multiverse becomes a labyrinth of what-ifs and time travel, just a way to peek down the paths not taken. But here's the twist: if these branches are infinite, how could we ever find our way back to the original timeline? And if time travelers keep splitting reality, could they dilute the fabric of existence itself? The math suggests no. The multiverse is bottomless, endlessly accommodating, yet it leaves us with a haunting question. In a cosmos where every possibility exists, does any choice truly matter? Or are we all just surfing the waves of an unfathomable quantum sea? One thing's certain: the many worlds interpretation doesn't just open a door to time travel, it blasts open the walls of reality itself. Stretching across the universe like invisible threads from the dawn of time, cosmic strings are theoretical cracks in spacetime itself, leftover scars from the universe's violent birth. These bizarre defects, thinner than an atom but denser than a neutron star, might be the ultimate cosmic shortcuts. Picture spacetime as a frozen lake. Most of its surface is smooth, but when the ice first formed, tiny fractures might have appeared, regions where the rules bend. Cosmic strings are like those cracks, except instead of ice, they're flaws in the very fabric of reality. And if two of these strings were to cross or loop, something extraordinary could happen. A closed timelike curve, bending time into a knot that could send you spiraling into the past. The math behind this is staggering. A single cosmic string might weigh more than an entire mountain range squeezed into a length smaller than a proton. That density warps spacetime so severely that traveling around the string in a precise spiral could let you circle back to an earlier moment, like a record needle skipping backward on a vinyl groove. Unlike wormholes or Tipler's cylinder, this wouldn't require exotic materials or infinite lengths, just the sheer gravitational pull of the string itself, twisting time like a wrung-out towel. But here's the catch: we've never detected a cosmic string directly. They're relics of the early universe, predicted by some models of quantum physics, but still missing from our cosmic inventory. If they exist, their faint gravitational signatures might lurk in the faint distortions of light from distant galaxies or the ripples of gravitational waves. Some theorists even suggest they could explain bizarre cosmic phenomena, like oddly aligned galaxy clusters or unexplained bursts of energy. What makes cosmic strings so tantalizing and terrifying is their raw power. A segment just 1 mile long could contain more mass than Earth, warping space around it into a natural time machine, yet their very nature makes them perilous. Get too close and tidal forces could shred matter atom by atom. Even if we found one, harnessing it would be like trying to ride a black hole, technically possible in theory, but requiring physics far beyond our grasp. Still, their existence would rewrite the rules of time travel. Forget bulky machines or spinning cylinders. A network of cosmic strings might already lace the cosmos, stitching together moments across eons. If we ever learn to navigate them, we might discover that the universe has been riddled with time loops all along, hidden highways through history, waiting for someone bold enough to take the first step. What if you could travel faster than light without actually moving at all? The Alcubierre drive offers a loophole in Einstein's cosmic speed limit by bending spacetime itself. Imagine standing on a moving walkway at the airport. The ground shifts beneath you, propelling you forward while you remain perfectly still. Now picture that same principle applied to the fabric of reality. Mexican physicist Miguel Alcubierre proposed this exact idea in 1994. A spacecraft nestled inside a warp bubble, where space-time contracts in front of it and expands behind it, effectively surfing a wave of distorted geometry. The ship itself never accelerates, dodging the relativistic effects of near-light-speed travel. It's not breaking the speed limit, it's cheating by folding the road. The mechanics are mind-bending. To create this warp bubble, you'd need something called negative energy, a hypothetical form of matter with repulsive gravity. Picture a cosmic trampoline. Ordinary matter like planets creates dips in spacetime, but negative energy would create a hill, pushing spacetime outward. Encase your ship in a ring of this exotic material, and you could theoretically compress spacetime ahead while stretching it behind, creating a pocket where distances shrink and time dilates on command. The math checks out. Alcubierre's equations are consistent with general relativity, but the practical hurdles are staggering. Estimates suggest the energy required might equal the mass energy of Jupiter. Even if we scaled it down, stabilizing the bubble and avoiding lethal radiation at the edges remain unanswered problems. Critics argue the Alcubierre drive leans too heavily on hypothetical physics. Negative energy has never been observed, though quantum mechanics allows for fleeting instances of it in phenomena like the Casimir effect, where microscopic gaps between plates exhibit negative pressure. Some models suggest modifying the bubble's shape could reduce energy needs, but we're still light years from engineering it. There's also the eerie side effect. Anything caught at the warp bubble's boundary would be hit with enough energy to incinerate planets, making arrivals as destructive as departures. Yet the concept holds a tantalizing promise. Unlike wormholes or cosmic strings, the Alcubierre drive doesn't rely on pre-existing cosmic oddities. It's a blueprint for building our own time machine. If perfected, it could whisk us to Proxima Centauri in weeks or send messages backward in time via manipulated spacetime. NASA Eagleworks lab even experimented with miniature warp field interferometers, though results remain speculative. The Alcubierre drive forces us to confront a radical truth. The universe might allow faster than light travel, not by defying its rules, but by rewriting the map entirely. Whether it's a dead end or a path to the stars, one thing's clear: the line between physics and fantasy has never been so thrillingly blurred. Black holes aren't just cosmic vacuum cleaners, they're nature's most extreme time machines. Picture the iconic scene from Interstellar where the crew orbits Gargantua, a supermassive black hole, and watches hours tick by for them while decades pass on Earth. That mind-bending time warp isn't just Hollywood flair, it's rooted in real physics. The closer you get to a black hole's event horizon, the point of no return, the more gravity warps space-time, stretching seconds into years for anyone watching from afar. It's time dilation cranked to 11. At the heart of this phenomenon is Einstein's general relativity, which tells us gravity isn't just a force, it's the curvature of space-time itself. A black hole's immense mass bends this fabric so severely that time itself slows down near it, like a clock submerged in molasses. To an outside observer, someone falling toward the event horizon would appear to move in slow motion, their signals redshifted and stretched until they seemingly freeze at the edge. But here's the twist: for the person falling in, time would feel normal. They'd cross the horizon in finite time, oblivious to the cosmic drama unfolding outside. This creates a paradox of perspective. If you could hover just outside the event horizon, say, on a ship like Interstellar's Endurance, you could theoretically witness the future of the universe flash before your eyes as time races ahead elsewhere. Want to see Earth in the year 3000? Orbit a black hole for a few hours and return to find centuries have passed, but venture too close and the tidal forces would spaghettify you, stretching atoms into ribbons before you ever reach the horizon. The real question is, what's beyond the event horizon? Some theories suggest black holes might contain wormholes, linking distant regions of space-time or even different universes. Others argue the singularity at their core might shred the laws of physics entirely, making time travel a one-way trip to oblivion. One thing's certain: black holes don't just bend time, they push it to the breaking point, forcing us to confront the outer limits of reality itself. So while we're far from booking a ticket to Gargantua, these cosmic monsters remind us that the universe's most thrilling mysteries are hidden in the darkest corners. If black holes are cosmic vacuum cleaners sucking everything in, white holes would be their polar opposites: cosmic fire hydrants blasting matter and energy outward at impossible speeds. Imagine a black hole running in reverse. Instead of an event horizon trapping light forever, a white hole's boundary refuses to let anything in. What falls into a black hole might erupt from a white hole, as if the universe itself hit rewind. These hypothetical objects aren't just sci-fi fluff, they emerge from the same equations of general relativity that predict black holes, dangling the tantalizing possibility that time's arrow might not point in just one direction. The idea ties into CPT symmetry, a cornerstone of modern physics suggesting the universe obeys certain mirrored rules. C stands for charge flipping particles to antiparticles, P for parity reversing spatial dimensions like a mirror image, and T for time. According to this symmetry, if you filmed a particle interaction and played it backward while also swapping left for right and matter for antimatter, the reversed version should still obey physics laws. White holes fit neatly into this puzzle as the time-reverse twins of black holes, like watching a video of a collapsing star run backward, with matter exploding outward instead of imploding. But here's where it gets wild. Some theorists propose white holes could be the other end of black holes, funneling swallowed matter into distant regions of spacetime or even alternate universes. Picture a drain pipe connecting two sinks. Black holes are the drain, white holes the spout. This could explain where black holes' vanished information goes, solving Stephen Hawking's famous paradox about whether data is truly lost in their depths. Others speculate that the Big Bang itself might have been a primordial white hole, bursting forth with the raw material of the cosmos. Yet for all their elegance, white holes face a glaring problem: thermodynamics. They'd violate the second law by decreasing entropy, essentially unmixing the cosmic omelette. Nature tends toward chaos, not order, making white holes seem like mathematical ghosts possible on paper but forbidden by reality. Some models suggest they could exist briefly as black holes die, evaporating via Hawking radiation before snapping shut. Others argue they might lurk in the distant future, once the universe's expansion has stretched spacetime thin enough for new physics to take hold. The most radical interpretation, white holes could anchor entire time-reversed universes where cause and effect flip and entropy flows backward. In this mirror cosmos, broken cups reassemble and smoke pours back into cigarettes. It's a dizzying thought, implying time might not have a preferred direction at all, just local arrows shaped by entropy's rise in our corner of reality. Whether white holes are relics of the Big Bang, quantum afterlives of black holes, or mere mathematical curiosities, they force us to confront a humbling truth. The universe might be far stranger than our intuition allows. After all, if spacetime can bend, why shouldn't it also fold, twist, or even run backward? The answer, like white holes themselves, remains just out of reach, a shimmering mirage at the edge of physics map, daring us to look closer. Tachyons are the rebels of particle physics, hypothetical particles that laugh in the face of Einstein's cosmic speed limit by moving faster than light from the moment they're born. Unlike ordinary matter, which needs infinite energy to reach light speed, tachyons would start their existence already breaking that barrier, zipping through spacetime like cosmic cheetahs. But here's the twist. According to relativity, anything moving faster than light would experience time backward. A tachyon's journey might look like a film reel played in reverse, arriving at its destination before it even departed. Imagine a tachyon message sent to your past self. It'd hit your receiver before you'd finished typing it, like an email that outruns your fingers. The math behind these particles is surprisingly sound. Equations in quantum field theory allow for tachyon solutions, but they come with a catch. Tachyons would have imaginary mass, a concept that's less about weight and more about how they'd interact with spacetime. Think of it like trying to measure the square root of a negative number. It's not impossible in theory, but it defies our everyday intuition. This imaginary mass would make tachyons behave bizarrely. The more energy you tried to slow them down, the faster they'd go, like a car that accelerates when you hit the brakes. Yet for all their theoretical intrigue, tachyons remain stubbornly absent from experiments. If they existed, they'd leave ghostly trails in particle colliders or distort energy fields in ways we've never observed. Some physicists argue their elusiveness is a cosmic safeguard because tachyons could create paradoxes that unravel causality. Picture a tachyon striking a detector, triggering an event that prevents its own creation. It's the grandfather paradox on a subatomic scale, where cause and effect spiral into chaos. The irony, even if tachyons exist, we might never detect them directly. Their backward time flow could mean they've already zipped through our detectors before we switch them on, leaving only echoes in the math. For now, they linger at the edge of physics, a tantalizing "what if" that reminds us the universe still holds cards it hasn't dealt. Whether they're a glitch in the equations or a hidden layer of reality, one thing's certain: tachyons prove that even the rules of time might have loopholes waiting to be found. What if you could hold a piece of time in your hand, not as a fleeting moment, but as a physical structure that repeats like a heartbeat? That's the mind-bending promise of time crystals, a bizarre form of matter that doesn't just exist in space, but dances to the rhythm of time itself. Unlike ordinary crystals, think diamonds or snowflakes, where atoms are arranged in repeating patterns across space. Time crystals tick through cycles in time, returning to their initial state over and over like a clock's pendulum swinging in perfect perpetual motion. The wildest part, they don't need energy to keep this rhythm going. It's as if you wound a watch once and it ticked forever without slowing down. Scientists first dreamed up time crystals in 2012, when Nobel laureate Frank Wilczek proposed the idea as a theoretical curiosity. Critics dismissed it as impossible, arguing it violated the laws of thermodynamics. After all, perpetual motion machines can't exist. But just 5 years later, labs at Harvard and the University of Maryland proved the skeptics wrong. Using chains of charged atoms chilled to near absolute zero and zapped with precise laser pulses, they created the first time crystals. These structures didn't just vibrate in response to the lasers, they locked into a rhythmic pulse of their own, a beat distinct from the external stimulus. Imagine tapping a drum and hearing it echo back at a different tempo, as if the drum had its own internal metronome. The key to their behavior lies in quantum entanglement, where particles become linked across space and time. In a time crystal, particles synchronize their states in a loop, flipping back and forth like a cosmic game of red light, green light. Even more surreal, time crystals are non-equilibrium matter. They never settle into a steady state, defying the universe's usual push toward disorder. It's like a droplet of water that refuses to evaporate, or a fire that burns forever without fuel. Now, picture harnessing this for time loops. While we're far from building a time machine, time crystals hint at systems that could store or process information in repeating cycles, like a DVD that plays itself backward and forward endlessly. Some theorists speculate they might even mimic closed timelike curves on a microscopic scale, creating pockets where causality stutters. Imagine a quantum computer using time crystals to perform calculations that ripple backward through their own history, solving problems by effectively rewriting their past. Of course, there are hurdles. Time crystals observed so far exist only in fragile quantum systems, barely lasting microseconds. Scaling them up would mean taming decoherence, the quantum kryptonite that makes entangled particles unravel. But the mere fact they exist reshapes our understanding of time's arrow. If matter can tick like a clock without energy, what other impossible phenomena might be waiting in the equations? Time crystals don't just challenge physics, they invite us to rethink reality's most fundamental rhythms. And who knows, one day, these strange, ticking structures might become the gears in a machine that bends time itself. Quantum entanglement is often called spooky action at a distance, but what if that spookiness isn't just about space, but time itself? Picture two particles born from the same quantum event, forever linked no matter how far apart they drift. Change the spin of one and its twin instantly flips too, even if light years separate them. Einstein hated this idea, calling it spooky because it seemed to break the cosmic speed limit. But here's the twist: entanglement might not just defy distance, it could scramble our understanding of cause and effect. Recent experiments have pushed this phenomenon into even weirder territory. In 2016, researchers at the University of Vienna sent entangled photons through a fiber optic network, then measured them in an order that shouldn't matter classically. Yet the results were mind-bending. The measurement of one photon appeared to influence its partner's state before the measurement even occurred. It's as if the universe was working backward, rewriting the past to match future observations. This isn't just particles talking faster than light. It's physics flirting with retrocausality, where effects might precede their causes. Think of it like a cosmic game of poker where you see your opponent's cards before you place your bet. In quantum mechanics, this backward flow isn't just possible, it might be fundamental. The delayed choice quantum eraser experiment takes this further. By manipulating entangled particles after they've been detected, scientists can seemingly erase past decisions, altering whether the particles behaved like waves or particles long after the fact. It's as if the present reaches into the past and tweaks the script. Critics argue this doesn't amount to time travel, or just a reshuffling of probabilities. But the implications are staggering. If quantum systems can blur the line between past and present, could we someday engineer entanglement to send messages backward in time? The math hints at tantalizing possibilities. Some models suggest arranging entangled particles in precise loops could create self-correcting causal circuits, where information circles back to its origin without paradox. Of course, scaling this up to human-scale time travel is a quantum leap away. Decoherence, the fragility of entangled states, makes maintaining these links fiendishly difficult outside controlled labs. Yet the mere fact that particles might dance to time's rhythm in reverse forces us to reconsider reality's deepest rules. After all, if the smallest building blocks of the universe don't play by classical time's rules, who's to say we can't learn their tricks? The quantum realm keeps whispering a radical secret. Time might not flow in one direction, it might just be waiting for us to untangle its knots. What if everything you see, every star, every planet, even your own hands, isn't truly three-dimensional, but a breathtakingly detailed illusion projected from a flat, two-dimensional surface? That's the radical claim of the holographic principle, a theory that suggests our entire universe might be a cosmic hologram. At its core, this idea proposes that all the information needed to describe reality isn't spread across three dimensions of space, but compressed onto a vast, distant boundary, like a celestial DVD encoding the entire show. And here's where it gets even wilder. If time itself is just part of this holographic illusion, could we rewrite the cosmic script, editing past events like scenes in a movie? The roots of this theory stretch back to black holes. In the 1970s, physicist Jacob Bekenstein discovered that a black hole's entropy, its hidden information, isn't proportional to its volume, but to the surface area of its event horizon. It's as if the black hole's interior is somehow projected from its two-dimensional boundary. Later, string theorists like Leonard Susskind and Gerard T. Hooft expanded this into the holographic principle, arguing that all physics in a region of space could be encoded on its outer surface. Picture a snow globe where the 3D scene inside is actually painted on the glass, except the glass is the edge of the universe, and the paint is quantum bits flickering at the Planck scale. Now apply this to time. If the past, present, and future are just holographic data on a 2D surface, then our experience of time's flow might be a kind of cosmic sleight of hand. Imagine flipping through frames of a flip book. Each page is static, but when you thumb through them, the illusion of motion emerges. Similarly, the universes now could just be one slice of a timeless hologram, with causality stitched together by the way information is processed. This challenges the very idea that the past is fixed. If the hologram's data can be rewritten, perhaps events we remember as unchangeable could be altered, like editing a pixel in an old photograph and watching the entire image update. Critics argue this leans too heavily on metaphor, and even if the universe is holographic, that doesn't mean we can access the source code to tweak reality. But some models in quantum gravity suggest otherwise. The AD/CFT correspondence, a mathematical bridge between theories of gravity and quantum fields, hints that changes on the holographic boundary could ripple into the 3D world. In theory, manipulating quantum entanglement patterns on the 2D surface might reconfigure events in our perceived past. It's not quite a time machine, more like a cosmic undo button if you could reach the keyboard. The implications are dizzying. Forget Marty McFly's DeLorean. Time travel under the holographic principle wouldn't involve moving through years, but reprogramming the universe's underlying data. Step on a butterfly in the Jurassic era, you're not hopping timelines, you're tweaking the pixels that compose history itself. Of course, we're light years from wielding that power, if it's even possible. But the mere idea reshapes how we see reality, not as an immutable block of space-time, but as a dynamic projection, flickering on the edge of something far stranger. The holographic principle doesn't just suggest time is an illusion. It whispers that reality itself might be more malleable than we ever dreamed. The Novikov self-consistency principle offers a bold answer to the headache of time paradoxes. What if the universe simply doesn't allow contradictions to happen? Proposed by Russian physicist Igor Novikov in the 1980s, this theory argues that any attempt to alter the past would be thwarted by the laws of physics, ensuring events remain consistent. Think of time as a river with an unbreakable current. You can splash around, but you can't reverse the flow. If you traveled back to kill your grandfather, some unseen force, a gun jamming, a sudden slip, a change of heart, would always intervene to keep history intact. The universe, in this view, is like a meticulous editor trimming any plot holes before they can unravel causality. This idea transforms classic paradoxes into closed loops of inevitability. Take the predestination paradox, where a time traveler's actions in the past turn out to be what always happened. Imagine going back to stop a fire, only to realize your panic caused the accident in the first place. Your future intervention was baked into history all along. Films like 12 Monkeys lean into this chilling inevitability, where every attempt to change events only tightens the knot of fate. Nabokov's principle suggests reality is self-correcting, with inconsistencies smoothed out before they can take root. Critics call this a cosmic cop-out, arguing it reduces free will to an illusion. If every time traveler's move is pre-scripted, are we just actors following a script written by physics? Yet the math has surprising support. Quantum mechanics shows particles can adjust their behavior to avoid contradictions, like electrons taking paths that prevent interference with their own past. The principle also aligns with Einstein's relativity, where spacetime is a single, unchanging block. What we experience as now might just be one slice of a prewoven tapestry. Here's where it gets eerie. In 2009, physicist Seth Lloyd proposed a quantum experiment where particles interact with their past selves, forcing outcomes that avoid paradoxes. The results: the system always found a consistent solution, like a chess game where every move checks but never checkmates itself. It's as if the universe prefers elegant loops over messy contradictions. The Novikov principle doesn't just protect time travel, it redefines it. No more worrying about erasing your existence or fracturing timelines. Instead, you'd be playing a role in a story that was always meant to unfold exactly as it does. Whether that's comforting or claustrophobic depends on how you view the ultimate scriptwriter, physics itself. Picture this: a struggling writer receives an anonymous manuscript in the mail, a masterpiece so brilliant it launches their career. Decades later, now a famous author, they decide to send that very manuscript back in time to their younger self, who originally wrote it. This is the bootstrap paradox, a mind-bending loop where information or objects seem to exist without any true origin. Like a snake eating its own tail, the chain of cause and effect twists into an infinite circle, leaving us scratching our heads over where or when it all began. Take the classic example of Shakespeare. Imagine a time traveler hands the bard a complete copy of Hamlet before he pens a single line. Shakespeare then publishes the play as his own work. Centuries later, the very same text is discovered and sent back to him. The play exists in flawless form, but who actually composed it? Not Shakespeare, since he merely copied it. Not the time traveler who simply delivered it. The words float in a causal void, uncoupled from any creator. It's like a song stuck in your head that you later realize you're humming from a recording of yourself humming it. The paradox gets thornier when applied to physical objects. Suppose a scientist invents a revolutionary time machine, but only after studying a model brought to her by her future self. The blueprints, materials, and knowledge all trace back to that borrowed device. Remove the time loop and the invention vanishes from history. Unlike the grandfather paradox, where changing the past creates contradictions, the bootstrap paradox presents a universe that's eerily consistent, just inexplicably hollow at its core. Physicists are divided on whether such loops could exist. Some argue they're mathematically plausible within general relativity's framework, where closed time-like curves permit self-consistent cycles. Others counter that quantum mechanics would intervene, with tiny fluctuations disrupting the loop. After all, nature abhors infinite regress. Every effect should have a cause, even if it's hidden in the quantum foam. Yet, intriguingly, certain quantum systems exhibit bootstrap-like behavior. with particles influencing their own past states in controlled experiments. The bootstrap paradox doesn't just challenge our notions of time, it questions the very nature of creativity and originality. If a symphony, invention, or idea can spiral through time without a true author, does that devalue it? Or does it reveal something profound about the universe's structure? That information, like energy, might simply rearrange itself in endless patterns. One thing's certain, in a cosmos riddled with temporal loops, the line between inspiration and illusion becomes beautifully blurred. Parallel universes offer a cosmic escape hatch from time travel's stickiest paradoxes. What if every choice we make doesn't just branch into a new future, but an entirely separate reality? The multiverse theory, a cornerstone of modern cosmology, suggests our universe might be one bubble in an infinite foam of alternate timelines, each one splitting off with every quantum decision. This isn't just about different versions of history, it's about rewriting the rules of causality itself. Take the grandfather paradox. Instead of vanishing in a puff of logic, a time traveler who alters the past would simply slide into a parallel timeline where their actions unfold without erasing their original world. It's like jumping from one train track to another, leaving the first rail untouched behind you. The quantum suicide thought experiment throws this into stark relief. Imagine a scientist rigging a gun to a quantum event, say, the decay of a radioactive atom. If the atom decays, the gun fires. If not, it doesn't. In a single universe view, the scientist has a 50-50 chance of survival with each trial. But in the multiverse, every possible outcome plays out somewhere. From the scientist's perspective, they'd always survive because the versions where they die cease to experience reality. Their consciousness simply follows the branching path where the gun never fires, creating the illusion of invincibility. Apply this to time travel, and the implications are staggering. Any catastrophic paradox might just shunt you into a timeline where the disaster never occurred, leaving you blissfully unaware of the alternate versions where things went horribly wrong. Films like Everything Everywhere All at Once and Sliding Doors flirt with these ideas, but the science goes even deeper. Some interpretations of quantum mechanics, like Hugh Everett's many worlds interpretation, argue that every quantum event, from an electron's spin to a human decision, spawns new universes. This means a time traveler stepping on a butterfly in the Cretaceous wouldn't erase birds from existence, they'd just create a new branch where dinosaurs still rule, while the original timeline hums along unchanged. Paradoxes dissolve into probability, with every possible outcome playing out across the multiverse's infinite tapestry. Critics argue this is less time travel and more universe hopping, but the distinction blurs at the quantum level. If all possible histories exist, then every past you could visit is already out there, waiting in some alternate reality. The real challenge, navigating the maze. Without a cosmic map, how would you find your way back to your original timeline? And if every choice spawns new branches, could you ever truly return to the world you left? Or would it forever be one universe over, just out of reach? The multiverse doesn't just solve time travel's paradoxes, it turns them into gateways, reminding us that reality might be vaster, stranger, and more forgiving than we ever dared imagine. We live in a world where moving through space feels effortless. You can walk forward, jump upward, or slide sideways with ease. But what if time is just another dimension we're constantly moving through, like a river carrying us from one moment to the next? This is the core idea behind treating time as the fourth dimension, woven together with space into a single fabric called space-time. Picture a grid not just with X, Y, and Z axes, but with a T axis representing time. Just as you'd navigate a city by moving through its streets, space-time suggests we're always traveling along this fourth axis, whether we realize it or not. Einstein's theories shattered the old view of time as an unchanging backdrop. Instead, relativity shows that time stretches and compresses depending on motion and gravity, like a rubber sheet warped by heavy objects. This merging of space and time into spacetime isn't just poetic, it's the foundation of modern physics. The block universe theory takes this further, proposing that past, present, and future all exist simultaneously like frames in a film strip. From this perspective, now is just where your consciousness happens to be, a moment in a vast, unchanging 4D structure where every event from the Big Bang to the heat death of the universe is already out there, fixed in place. Imagine spacetime as a loaf of bread, with each slice representing a snapshot of the universe at a particular moment. Normally, we experience these slices one after another, but what if you could step outside the loaf and move freely between slices? That's the tantalizing promise hidden in 4D geometry. Some models even suggest advanced civilizations might manipulate spacetime's curvature to shortcut across time, treating it like a landscape to traverse rather than a one-way current. Critics argue this view drains life of its dynamism, reducing free will to an illusion. If the future's already written in the block universe, are our choices real? Others counter that our experience of time's flow might emerge from deeper quantum processes, like how temperature arises from atoms' motion. Either way, seeing time as a dimension reshapes what's possible. It hints that with the right tools, we might one day navigate time as readily as we cross a street, turning the fourth dimension from a prison into a playground. Time isn't just a cosmic backdrop. It's a deeply personal experience shaped by the quirks of your own brain. Ever noticed how a minute can drag during a boring lecture but vanish in a flash when you're having fun? That's your consciousness playing tricks with time. Neuroscientists call this time perception. And it's not just psychological, it's biological. Your brain doesn't passively count seconds like a clock. It constructs time from a symphony of sensory inputs, memories, and chemical signals. And when you tweak those signals, whether through meditation, adrenaline, or even psychedelics, time can stretch, warp, or even shatter entirely. Take the classic example of car accidents. Survivors often describe events unfolding in slow motion, as if time itself had gummed up. Studies suggest this isn't just hindsight, it's a survival mechanism. Under extreme stress, the brain's amygdala kicks into overdrive, flooding the system with neurotransmitters that hyper-focus attention. Like a camera switching to high-speed mode, your brain crams more perceptual data into each moment, creating the illusion of time dilation. Meanwhile, dopamine, the brain's reward chemical, has the opposite effect. When you're engrossed in a thrilling game or conversation, dopamine speeds up your internal clock, making hours feel like minutes. Now imagine hacking this system intentionally. Meditation masters, for instance, can enter states where time seems to dissolve entirely. Brain scans of experienced monks reveal reduced activity in the parietal lobe, a region that helps anchor us in linear time. Without that anchor, moments blur into a timeless now, a hint that consciousness might hold the keys to bending time's flow. Psychedelics like psilocybin or LSD take this even further, scrambling the brain's timekeeping networks. Users report episodes where minutes feel like eternities, or where past, present, and future smear together like wet paint. The implications are staggering. If consciousness shapes time perception, could we one day learn to control it like a dial? Technologies like transcranial magnetic stimulation already let scientists tweak neural activity with precision. Pair that with advances in neurofeedback, and you might someday train your brain to stretch deadlines or savor moments longer. Of course, we're nowhere near building a neural time machine, but the mere fact that our minds can warp time at all suggests reality's clockwork might be more flexible than we think. After all, if a mushroom or a meditative trance can bend your sense of time, what other illusions might be waiting to unravel? This isn't just about altered states, it's about the nature of time itself. Physics treats time as a dimension, but your brain treats it as a story woven from attention, memory, and chemistry. Master those threads and who knows? You might not need a wormhole to time travel, just the right state of mind. What if you could slow down or speed up time inside a machine, not by traveling to a black hole or bending space-time, but by manipulating time's flow right here on Earth? This is the audacious promise of artificial time dilation, the idea that we might one day engineer devices that control time's passage locally like a cosmic dimmer switch. Forget flux capacitors and DeLorean's real-world science is already flirting with this possibility, and the implications are staggering. Take atomic clocks, the most precise timekeepers ever built. These devices measure time by tracking the vibrations of atoms cesium or rubidium, with such accuracy that they lose less than a second over millions of years. But here's the twist: when you place two atomic clocks at different altitudes, like one on a mountain and another at sea level, they tick at slightly different rates. The higher clock runs faster because Earth's gravity weakens with distance, warping time ever so slightly. It's a minuscule effect, but it proves a profound point: time isn't absolute. It's malleable, and if gravity can stretch it, why couldn't we? The challenge is scaling this up. Imagine a chamber where time flows at half the speed of the outside world. Step inside, and an hour for you would feel like 2 to everyone else. Sci-fi has toyed with this for decades, from Interstellar's tidal wave planet to the Time Machine's laboratory. But the real breakthrough might lie in metamaterials, engineered substances with properties not found in nature. Some researchers speculate that carefully structured metamaterials could manipulate electromagnetic fields in ways that mimic extreme gravity, effectively creating time lenses that slow or accelerate local time. Pair that with quantum entanglement, where particles influence each other instantly across space, and you've got a recipe for controlled time warps, at least in theory. Of course, the hurdles are immense. The energy required to distort time measurably could dwarf anything our civilization can muster. There's also the causality problem. If you slow time inside a box, could information leak out, creating paradoxes? Experiments with time crystals, structures that repeat in time like latticework, hint that time's fabric might be more pliable than we thought, but we're still light years from a functional time dilation device. Yet the mere possibility reshapes our understanding of time. If we could tweak its flow, even fractionally, the applications would revolutionize everything from computing to space travel. Supercomputers could process data in slowed time, making years of calculations pass in days. Astronauts might endure decades-long voyages while aging only months. And for those dreaming of glimpsing the future, a time dilation chamber could offer the next best thing, a window where patience turns into time travel. The dream isn't just to ride time's current anymore, it's to bend the river itself. Dark matter is the universe's greatest unsolved mystery, an invisible substance that outweighs ordinary matter 5 to 1, yet refuses to reveal itself except through its gravitational pull. We know it's there because galaxies spin faster than they should, and light bends around cosmic voids where nothing visible exists. But what if this shadowy force isn't just shaping space, it's twisting time itself? Some physicists speculate that dark matter's hidden properties might create subtle time warps, like invisible whirlpools in the fabric of reality. Imagine a river where most of the current flows beneath the surface, undetectable from the shore but tugging everything along with it. That's the eerie possibility lurking in dark matter's gravitational grip. Take the bullet cluster, one of the most compelling pieces of evidence for dark matter's existence. When two galaxy clusters collided, their visible gas clouds slammed together and slowed down, but their gravity kept moving full speed ahead, as if anchored to something unseen. This something is presumed to be dark matter, streaming through the wreckage like a ghostly tide. Now, if dark matter can bend light and defy expectations this dramatically, could it also stretch or compress time in ways we haven't measured yet? Einstein taught us that gravity slows clocks. Satellites in orbit tick faster than those on Earth's surface. Dark matter's gravitational fields, though diffuse, are everywhere woven through galaxies in vast halos. Over cosmic distances, even tiny time distortions could add up, like a watch gaining seconds each day until it's years ahead. Dark energy, the even more enigmatic force accelerating the universe's expansion, throws another wrench into the mix. If dark energy is stretching spacetime itself, could it also be diluting time's flow on a universal scale? Some models suggest that in regions where dark energy dominates, time might thin out like soup stretched too far, making the distant future rush toward us faster than we expect. It's as if the universe has hidden levers controlling time's speed, and we're only now fumbling in the dark to find them. Of course, proving this is a monumental challenge. Dark matter doesn't emit, absorb, or reflect light. It's only felt through gravity. To detect its effects on time, we'd need clocks precise enough to catch infinitesimal variations across galactic distances. Yet the hunt is already on. Experiments like the atomic clock ensemble in space aim to measure time's passage in orbit with unprecedented accuracy, watching for anomalies that might hint at dark matter's unseen hand. Other researchers are simulating how dark matter clumps could create localized time eddies, like invisible whirlpools where clocks tick just a hair out of sync. The most tantalizing idea: if dark matter interacts with time differently than ordinary matter, it might explain why we've struggled to detect it through conventional means. What if it's not just hiding in space but in the gaps between moments, whether it's bending time or simply revealing how much we still don't understand? Dark matter reminds us that the universe's clockwork might be far stranger than we ever imagined. And if we ever crack its code, we might find that time travel wasn't something we invented, but something we discovered, hidden in the dark all along. Deep in the fabric of the universe, beneath atoms and quarks, lies what physicists call the vacuum state, not the emptiness of space, but the lowest possible energy level where quantum fields like the Higgs field settle into stability. Or so we thought. What if our universe isn't in true stability at all, but perched precariously on a false ledge, like a ball balanced at the top of a hill? This is the unsettling premise of vacuum metastability, the idea that our cosmos might be a cosmic accident waiting to happen, and if it tips, time itself could reset in an instant. The Higgs field, famous for giving particles their mass, is the key player here. In our current universe, it sits at what's called a local minimum, a dip in the energy landscape that seems stable but isn't the lowest possible point. Picture a valley surrounded by higher mountains. We're sitting comfortably in that valley, unaware there might be a far deeper chasm just beyond the ridge. If something jostled the Higgs field hard enough, say an extreme quantum fluctuation or an ultra-high energy collision, it could theoretically tumble into that lower state, unleashing a cataclysm known as a false vacuum decay. This wouldn't be an ordinary explosion. A bubble of true vacuum would erupt at light speed, rewriting the laws of physics as it expands. Inside this bubble, the Higgs field's new value would reshape fundamental forces, potentially dissolving atoms, altering the speed of light, or even redefining time itself. The shockwave wouldn't just destroy matter, it would reboot reality, erasing the past as effectively as slamming Ctrl+Alt+Delete on the cosmos. One moment you're sipping coffee, the next there's no you, no coffee, just a new universe with rules we can't begin to predict. The terrifying beauty of this scenario: it could already be happening. Quantum fluctuations mean such bubbles might spontaneously form anywhere, anytime. If one appeared in some distant galaxy, we'd never see it coming. The boundary would reach us at the speed of light, offering no warning. Some calculations suggest our universe's Higgs field is just stable enough to last billions of years. But stable enough is a shaky reassurance when the stakes are existence itself. Yet there's a twist: if a vacuum decay did occur, it might not be the end. The new vacuum state could birth a fresh universe with its own arrow of time, effectively resetting the clock. In this wild scenario, time travel wouldn't require machines or wormholes, just the universe's own capacity for reinvention. It's less going back and more starting over, with every prior moment erased like chalk from a blackboard. Critics argue this is more existential hazard than practical theory. After all, if it happens, there's no one left to debate it. But the implications are profound. If our universe is metastable, it hints at a multiverse where other bubbles with different physics and timelines might exist beyond our cosmic horizon. It also forces us to grapple with time's fragility. We think of it as an immutable river, but the vacuum metastability event suggests it's more like a pane of glass solid until the moment it shatters, leaving only echoes of what flowed before. Have you ever rounded a corner and suddenly found yourself somewhere, or someone that shouldn't exist? Across the globe, people report eerie moments where time itself seems to glitch, dropping them into scenes from the past or future before snapping back to reality. Among the most famous is the Versailles incident of 1901, when two British academics, Charlotte Moberly and Elena Jourdain, claimed to wander the palace gardens only to stumble into the court of Marie Antoinette. They described encountering figures in 18th century dress, hearing unfamiliar music, and even smelling wood smoke from long extinguished fires, details so vivid they later wrote a book detailing their experience. Skeptics dismiss it as a shared hallucination or mistaken identity, but the sheer specificity of their account keeps this mystery alive over a century later. Time slips aren't confined to historic landmarks. In Liverpool, England, a taxi driver named Frank in 1979 swore he picked up a fare dressed in outdated clothing, only for the passenger to vanish mid-conversation, leaving behind a newspaper from 1956. In New York's Times Square, a woman named Ruth in the 1980s reported stepping off a subway train into a version of the city where cars and clothing looked decades older, a vision that dissolved minutes later. These stories share uncanny similarities: sudden disorientation, hyper-realistic sensory details, and an abrupt return to the present, often leaving witnesses shaken and questioning their sanity. Psychologists offer plausible explanations, from temporal lobe epilepsy, which can trigger vivid hallucinations, to the brain's knack for pattern recognition gone awry. When we're in familiar places steeped in history, like Versailles or old city streets, our minds might unconsciously reconstruct the past using ambient cues, creating a fleeting timescape woven from memory and imagination. The brain is a relentless storyteller, stitching together fragments to fill gaps in perception. Add fatigue, stress, or even electromagnetic fluctuations, and you've got a recipe for reality bending. Yet paranormal researchers counter with a wilder possibility. What if these glitches are evidence of thin spots in space-time? Quantum physics allows for microscopic fluctuations where particles briefly tunnel through barriers or pop in and out of existence. On a macro scale, could similar instability open transient windows between eras? Some theories suggest Earth's geomagnetic fields, or ley lines, might concentrate energy in ways that briefly warp local time, like a cosmic short circuit. Others propose that intense emotional imprints, say, from traumatic historic events, could leave a sort of psychic residue, replaying like a haunted recording under the right conditions. The truth might lie somewhere in between. While most time slips can be chalked up to quirks of neurology, the handful that defy easy explanation keep the debate alive. Whether glitches in the matrix or glitches in the mind, these stories remind us that time's grip on reality might be more tenuous than we think. After all, if consciousness can stretch and warp time's flow, who's to say the universe doesn't sometimes slip up too? What if every time you close your eyes at night, you're not just dreaming, you're time traveling? The idea that dreams could be portals to alternate realities or glimpses of other timelines isn't just the stuff of sci-fi. It's a theory gaining traction among neuroscientists and physicists alike. Think about those inexplicable dreams where you're someplace unfamiliar yet eerily detailed. or moments of déjà vu so strong they feel like echoes of a life you've already lived. Could these be fragments of parallel existences bleeding into your subconscious? Lucid dreaming adds fuel to the fire. For those who master it, lucid dreaming is like grabbing the steering wheel in the middle of a nighttime journey. You become aware you're dreaming and can consciously shape the experience. Some practitioners report visiting hyper-realistic dreamscapes with consistent geography, even returning night after night to explore further. In one striking case, a seasoned lucid dreamer described wandering a bustling medieval city, interacting with characters who seemed fully autonomous, only to later discover architectural details matching historical records of a place they'd never studied. Coincidence or something far stranger, the science behind this is as fascinating as it is speculative. Quantum physics suggests that at the subatomic level, particles exist in multiple states until observed, a principle called superposition. Some theorists, like physicist Fred Alan Wolf, propose that dreams might tap into this quantum uncertainty, allowing the brain to sample alternate versions of reality where different choices led to different outcomes. It's as if your sleeping mind becomes a radio tuning into frequencies of timelines just out of phase with your own. Then there's the biological angle. During REM sleep, the brain's timekeeping mechanisms go haywire. The suprachiasmatic nucleus, our internal clock, slows down while the hippocampus, the seat of memory, fires wildly, stitching together fragments of experience into narrative. This could explain why dreams feel timeless. Minutes in reality stretch into hours in the dream world, and distant memories surface alongside future anxieties. But what if this neural chaos isn't just random noise? What if it's the brain's way of sifting through the multiverse, assembling pieces of lives unlived? Skeptics argue these experiences are just the brain's storytelling at work, weaving memories and imagination into surreal tapestries. Yet the consistency of certain accounts raises questions. Cultures worldwide share myths of dreamwalkers and prophetic visions, from Aboriginal Australians' dream time to Norse legends of Odin traversing realms in his sleep. Modern experiments add intrigue. In controlled studies, some lucid dreamers have demonstrated the ability to send simple messages or images to waking participants, hinting at a blurrier line between dreams and shared reality than we've assumed. Whether dreams are cosmic voyages or neural misfires, one thing's clear: they challenge our understanding of time's rigidity. If consciousness can bend time's rules behind closed eyelids, maybe the past and future aren't as distant as they seem. And for those chasing the ultimate lucid dream, the next frontier might not just be controlling the dream, but learning where or when to point it. What if the secret to time travel isn't hidden in black holes or quantum equations, but coiled inside your very DNA? The idea that biology might hold echoes of the past or even blueprints of the future sounds like science fiction, but some scientists argue that evolution itself could be a kind of time machine. Imagine your genes as a scrapbook, not just of your ancestors' traits, but of their experiences, traumas, adaptations, even fragmented memories passed down through generations like a whispering chain stretching back millions of years. This isn't just about inherited eye color or a predisposition for allergies. It's about the haunting possibility that time leaves fingerprints in the fabric of life itself. Take the phenomenon of epigenetic inheritance. Studies show that famine survivors, war veterans, or even those who endured extreme stress can pass chemical markers attached to their DNA to their children and grandchildren. These markers don't alter the genetic code itself, but act like volume knobs, turning genes on or off in response to ancestral environments. Dutch famine victims in the 1940s, for example, bore descendants with higher rates of obesity and diabetes, as if their bodies were preparing for a scarcity that never came. It's as if time folds backward through biology, letting the past nudge the future. But what if this goes further? Biologist Rupert Sheldrake's controversial theory of morphic resonance takes this a step into the surreal. He proposes that nature has a kind of collective memory, a field of information that shapes habits, instincts, and even physical forms across time and space. When rats in a lab learn a new maze faster because other rats elsewhere have already mastered it, or when monarch butterflies inherit migration routes they've never flown, Sheldrake argues it's evidence of a living tapestry where time isn't linear but woven. Critics dismiss this as pseudoscience, but it raises a provocative question. Could evolution be less about random mutation and more about tapping into a reservoir of ancestral knowledge? Consider the eerie precision of animal instincts. How do salmon return to the exact streams of their birth after years at sea? Or how do birds navigate by starlight they've never seen? Mainstream science points to magnetoception and celestial cues, but some theorists wonder if these creatures are accessing something deeper, a biological Wi-Fi connecting them to the past. Even human déjà vu might be more than a neural glitch. Could it be a flicker of genetic memory, a fleeting overlap with an ancestor's lived moment? Then there's the speculative edge of biotemporality, the idea that DNA might encode not just information but temporal information. Some experiments suggest bacterial DNA can exhibit quantum coherence where particles exist in multiple states at once. If true, might our genes harbor fragments of timelines we've never lived but somehow remember? Indigenous cultures have long spoken of dreaming ancestors or walking in the footsteps of those who came before. Modern genetics might be catching up to what intuition has whispered for centuries, that time isn't just outside us but within. Whether these theories hold water or not, they reframe time travel from a mechanical feat to a biological birthright. The past might not require a machine to visit, just the right key to unlock what's already written in the cells. And if that's true, then every heartbeat, every instinct, every strange dream of a place you've never been might be a ripple from a one you've never lived. The real question isn't whether biology can time travel, it's how much we're willing to listen to what it's trying to tell us. What if your entire reality, every memory, every moment wasn't the original run, but a replay? Digital time travel flips the script on conventional theories by suggesting we might already live inside a simulation where the past and future are just lines of code waiting to be tweaked. Philosopher Nick Bostrom's seminal simulation argument lays the groundwork. If advanced civilizations could one day create ancestor simulations so detailed they're indistinguishable from reality, the statistical likelihood is that we're inside one of those simulations rather than the base reality. Think of it like this: if there's a 1 in a trillion chance a single civilization reaches this technological zenith and decides to run even a handful of simulations, the number of simulated minds would dwarf those in the real world. Suddenly, the odds you're living in the original universe shrink to near zero. This isn't just abstract philosophizing. If we're in a simulation, time travel could be as simple as loading a saved file. Imagine the universe as a hyper-advanced version of The Sims where the programmers, or even privileged users, could rewind events to any point, adjust variables, and hit play again. Historical anomalies like déjà vu or the Mandela effect might not be glitches in our memory but patches or rollbacks in the simulation's code. Even quantum mechanics' bizarre behavior, where particles seem to exist in multiple states until observed, could be explained by rendering limitations, the simulators optimizing processing power by only loading details when needed. The implications are dizzying. Simulations could contain nested layers, universes within universes, each with their own rules. A time traveler might just be an entity from a higher-level simulation accessing our layer's debug menu. And if time is procedural, like a generative AI building history as we observe it, altering the past wouldn't create paradoxes. It would just trigger a recalculation, like editing a spreadsheet and watching the formulas update. But there's a catch. If the simulators wanted to hide their work, they'd likely code restrictions to prevent us from detecting or manipulating the system. This might explain why time travel remains elusive. It's not a physics problem, but a permissions issue. Still, glitches could slip through. Some theorists point to unexplained phenomena like the double-slit experiment's observer effect or quantum entanglement as potential breadcrumbs, hints that reality is pixelated at its core. The most unsettling question isn't whether we can time travel, it's whether someone or something already has. If history is just a replayable construct, our entire existence might be an experiment watched by higher dimensional users who can pause, rewind, or reset the simulation on a whim. Whether that's liberating or terrifying depends on one thing. Do we want to peek behind the code? And if we do, will the simulators let us? Long before Einstein penned his equations or physicists dreamed of wormholes, our ancestors wove tales of doorways to other times, stories so vivid they blur the line between myth and forgotten truth. Take the Pushpaka Vimana from India's ancient Ramayana, a flying chariot described with uncanny precision, jewel-encrusted, capable of crossing continents in hours and piloted by the god King Rama. Texts claim it could ascend beyond the sky and travel to the place where the sun rises and sets in the same moment, phrases that sound suspiciously like orbital flight or bending time itself. Modern scholars dismiss it as poetic metaphor, but when you compare these accounts to other global legends, patterns emerge that defy easy explanation. The Aboriginal Dreamtime speaks of sky heroes who walk through sacred rocks to enter alternate realms, returning with knowledge of future events. Norse myths tell of Bifrost, a rainbow bridge allowing gods to traverse not just space but eras. Even Plato's Atlantis narrative hints at advanced technology lost to time, with the philosopher describing a portal of Cronus where past and future converged. These aren't isolated fantasies, they're recurring motifs across cultures that never interacted. How did ancient societies separated by oceans and millennia dream up such similar concepts without a shared frame of reference? Consider the Irish legends of the Shia fairy mounds said to house portals where time flows differently. Mortals who stumble in might emerge centuries later, their bodies untouched by age. Japanese folklore mirrors this with Yorishima Taro, a fisherman who visits an undersea palace for what feels like days, only to return home 300 years in the future. The consistency is chilling. Whether it's Celtic hollow hills or Hindu celestial vehicles, the core idea persists: specific locations or objects could warp time's fabric. Modern archaeology adds fuel to the fire. The Bajra caves in India contain carvings dated to 200 BC showing figures riding wheel-less aerodynamic vehicles eerily resembling contemporary UFO reports. Mayan temples align with celestial events with precision that would require knowledge of orbital mechanics. And then there's the Antikythera mechanism, a 2,000-year-old Greek device considered the world's first analog computer, capable of predicting astronomical positions decades in advance. Were these flukes of ingenuity or fragments of lost science that once understood time as something malleable? Skeptics argue these are coincidences amplified by hindsight bias. Yet when you stack the evidence, ancient texts describing flight and temporal distortion, artifacts demonstrating impossible technology, oral traditions warning of time's thin places, the weight becomes harder to shrug off. Maybe our ancestors weren't just spinning fables. Maybe they were recording encounters with phenomena we're only now beginning to theorize about. The most tantalizing question isn't whether these myths contain truth, but how much truth we've forgotten along the way. Government documents stamped classified have long been a breeding ground for time travel lore, especially when real-world experiments sound stranger than fiction. The infamous Philadelphia experiment is a perfect storm of secrecy and speculation. According to conspiracy theories, in 1943, the U.S. Navy allegedly used Einstein's unified field theory to render the USS Eldridge invisible, only for the ship to teleport, or even time travel before reappearing with crew members fused into bulkheads or driven insane. Declassified records do confirm Navy research into degaussing, a process to make ships undetectable to magnetic mines, but the logs show no evidence of space-time manipulation. Yet the myth persists, fueled by eerie details like sailor testimonies and a mysterious researcher named Dr. Franklin Reno, who may have been a composite of real scientists. The line between military secrecy and science fiction blurs further with the Montauk Project, a supposed sequel to Philadelphia involving mind control, interdimensional portals, and even a shadowy figure named Duncan Cameron who claimed to hop between timelines. Skeptics point out that Montauk's lore emerged decades later, woven from unreliable accounts and a dose of outright fabrication, but that hasn't stopped UFO enthusiasts from citing declassified CIA files on psychic experiments as proof of deeper truths. The real intrigue lies in how these stories mutate. Take Operation Paperclip, which brought Nazi scientists to America, a factual program that conspiracy theorists linked to time travel research, suggesting recruited minds like Werner von Braun worked on secret chronotech. Files show these scientists focused on rockets, not time machines, yet the grain of truth government cover-ups gives the fantasy legs. Even the CIA's Stargate project, which explored remote viewing in the 1970s, gets twisted into evidence of temporal espionage, despite documents revealing it was scrapped for inconsistency. The pattern is clear. When governments shroud projects in classified tape, imagination rushes to fill the gaps. But here's where critical thinking kicks in. For every wild claim, there's often a mundane explanation wrapped in bureaucratic mystery. The Philadelphia experiment's most cited witness, Carl Allen, later admitted to fabricating parts of his story. Montauk's central figures have backgrounds riddled with contradictions, yet the persistence of these tales raises a deeper question. Why does the idea of hidden time travel programs captivate us? Perhaps it's the thrill of imagining that world-changing tech exists just beyond public reach, or the fear that if time manipulation were possible, of course it'd be locked away. The truth may be less dramatic, but no less fascinating. Real history is full of experiments bizarre enough without adding time loops to the mix. So while no declassified file confirms a working time machine, the intersection of military secrecy and myth-making reveals something profound about human nature. We don't just want time travel to be real, we want to believe it's already here, lurking in vaults we aren't cleared to see. And in a way, that's its own kind of time capsule, a snapshot of our endless fascination with bending the rules of reality. Long before physicists pondered wormholes or quantum loops, ancient scriptures and sacred texts were already wrestling with the idea of transcending time. Take Hinduism's concept of Kala, the god of time, who is both the destroyer and the architect of cycles within cycles, days turning into epochs, epochs dissolving into cosmic nights. The Rig Veda describes time as a wheel with 12 spokes, turning endlessly, while the Mahabharata speaks of King Kakadmi, who visited the heavens for a brief audience with the creator Brahma, only to return to Earth and find centuries had passed. This isn't just myth, it's a theological blueprint for time dilation, echoing Einstein's relativity thousands of years before the theory was penned. Christianity and Judaism grapple with timelessness in their own ways. The Bible's book of Revelation paints a vision where the Alpha and Omega, the beginning and the end, exist simultaneously in God's realm. Prophets like Elijah and Enoch are said to have been taken up into divine timelessness, bypassing death altogether. Then there's the curious case of Ezekiel's chariot, a fiery vehicle described with such mechanical precision that some scholars speculate it might represent an ancient encounter with advanced technology, or a metaphor for traversing spiritual dimensions beyond linear time. Buddhism and Jainism take a different approach, framing time as an endless spiral of cause and effect. The doctrine of karma isn't just about moral accounting, it's a temporal feedback loop where actions in one lifetime ripple into future rebirths. Tibetan Buddhists speak of tulkus, enlightened beings who consciously choose their reincarnations, retaining memories of past lives as if flipping through chapters of a single, unbroken story. It's a form of psychological time travel where the self transcends individual lifespans to navigate centuries. Even indigenous traditions hold startling insights. The Hopi people describe time as a layered tapestry where past and future events exist concurrently in the Great Spirit's perception. Their rituals often involve stepping outside of time to commune with ancestors or foresee coming droughts. Similarly, Australian Aboriginal Dreamtime isn't just a creation myth, it's a living dimension where ancestral beings continue to shape the present, blurring the line between history and now. What ties these traditions together is the audacious claim that time, as we experience it, is an illusion, a veil that can be lifted through devotion, meditation, or divine intervention. Whether it's Hindu yogis slowing their heartbeat to near suspension or Christian mystics like Saint Teresa of Avila describing visions that spanned millennia, the message is the same: the sacred doesn't obey clocks. Modern physics might frame time as a flexible dimension, but spirituality got there first, offering something science still struggles with: a why. If time can be bent, perhaps it's not just for exploration, but for revelation. Critics dismiss these accounts as allegory or wishful thinking, yet the parallels across isolated cultures are hard to ignore. Maybe prophecy isn't about predicting the future, but accessing a vantage point where past, present, and future are equally visible. Or perhaps, as some quantum theorists now suggest, consciousness itself is the missing link, the observer that collapses time's waveform into a single, flowing moment. Either way, the spiritual quest to conquer time reveals a profound truth. Humanity's oldest dreams might still hold the keys to its newest frontiers. What if the Big Bang wasn't the beginning, but just the latest reboot in an endless cycle of cosmic death and rebirth? This is the spine-tingling premise of conformal cyclic cosmology, a theory pioneered by Nobel laureate Roger Penrose that reimagines the universe's timeline as an infinite Ouroboros, a snake devouring its own tail. According to this model, our universe's fiery birth wasn't a one-time event, but one link in a chain stretching eternally forward and backward. As the cosmos expands into heat death, a cold, lifeless void where even black holes have evaporated, the very conditions that spawned the Big Bang re-emerge, resetting the clock for a new cycle. Time, in this view, isn't a straight line but a Möbius strip where the end folds seamlessly into the beginning. Penrose's math hinges on an elegant sleight of hand. At the universe's extremes, both the infinitely dense Big Bang and the infinitely stretched heat death, the laws of physics simplify to identical states. Gravity vanishes, particles lose mass, and spacetime itself becomes featureless. Like a film reel melted down to blank celluloid, the cosmos sheds all structure, allowing it to transition into a new cycle without residue from the old. This conformal rescaling means the universe's death isn't an end, but a cosmic palate cleanser. And here's where time travel enters the picture. If information from one cycle could survive this reset, it might imprint onto the next like a watermark, creating echoes of past universes in our own. Remarkably, Penrose claims to have found these echoes. His team identified concentric rings in the cosmic microwave background, the afterglow of the Big Bang, that he argues are gravitational shockwaves from collisions between supermassive black holes in the previous universe. These Hawking points are like cosmic bruises, lingering evidence of a cycle before ours. If true, it means the universe might carry memories of its own history across rebirths, like a phoenix remembering fragments of its past lives as it rises from the ashes. This reshapes time travel from a local phenomenon to a cosmic inevitability. In a cyclic universe, you wouldn't need a machine to visit the past, you just need to wait for the next cycle to replay it. Imagine a civilization in a future epoch decoding the cosmic microwave background like a celestial vinyl record, extracting data from universes long gone. Or consider the chilling possibility that our own actions might ripple forward into the next cycle, turning karma into a thermodynamic principle. Every choice, every event could become a fractal thread woven into the fabric of eternity. Critics argue that conformal cyclic cosmology stretches speculative physics to its limits. The idea that information could survive a Big Bang, let alone be detectable flies in the face of traditional thermodynamics. Yet Penrose's model offers something rare, a testable hypothesis. Those anomalous rings in the cosmic background are either statistical flukes or revolutionary evidence, and future telescopes like the James Webb may settle the debate. Whether proven or not, the theory forces us to confront time's grandest scale. If the universe is cyclical, then time isn't just bendable, it's recyclable. The past isn't lost, it's waiting in the wings, ready for its encore. And if Penrose is right, we're not just stardust, we're echoes of a universe that came before and blueprints for one yet to come. The ultimate time machine might not be a device, but the cosmos itself, eternally rewriting its own story. From black holes bending time like taffy to quantum particles flipping causality on its head, we've journeyed through 30 theories that stretch reality to its limits. Who would have thought Einstein's equations could predict time loops, or that your dreams might be tapping into parallel timelines? The sheer audacity of these ideas, wormholes stitching together distant eras, cosmic strings twisting space-time into knots, entire universes cycling through endless rebirths, proves truth isn't just stranger than fiction. It's wilder than our wildest fantasies. What makes these theories so thrilling isn't just their mind-bending math, but how they blur the line between lab coats and Hollywood scripts. Time crystals pulse like sci-fi gadgets, while the many worlds interpretation feels ripped from a multiverse blockbuster. Even ancient myths whisper secrets that modern physics is only now decoding. It's as if the universe is daring us to keep questioning, to keep pushing beyond impossible. But here's where you come in. Which theory hooked you the most? Was it Alcubierre's warp drive, where space-time surfs like a wave, the chilling possibility of universe-ending vacuum decay? Or maybe the eerie time slips that make you side-eye your own déjà vu? Drop your vote in the comments. We want to hear which concept blew your mind widest open. One thing's certain, the hunt to unravel time's mysteries is far from over. Every equation, every experiment, every crazy thought experiment brings us closer to answers we can't even imagine yet. So if your brain's still buzzing from these ideas, hit that subscribe button, because this is just the beginning. The cosmos has way more tricks up its sleeve, and we'll be here to unpack every one of them. Until next time, keep looking upward, inward, and occasionally backward through time. Who knows what you might